Relations and functions. Introduction. The concept of the term relation in mathematics has been drawn from the meaning of relation in English language, according to which two objects or quantities are related if there is a recognizable connection or link between the two objects or quantities. Let A be the set of students of class 12 of a school and B be the set of students of class 11 of the same school. Then, some of the examples of relations from A to B are given below. Types of relations. We know that a relation in a set A is a subset of A cross A. Thus, the empty set phi and A cross A are two extreme relations. For illustration, consider a relation R in the set A is equal to 1, 2, 3, 4, given by R is equal to A, B is to A minus B is equal to 10. This is the empty set, as no pair A, B satisfies the condition A minus B is equal to 10. Similarly, R dash is equal to A, B is to mod A minus B greater than or equal to 0 is the whole set A cross A, as all pairs A, B in A cross A satisfy mod of A minus B greater than or equal to 0. These two extreme examples lead us to the following definitions.
Definition 1. A relation R in a set A is called empty relation if no element of A is related to any element of A. That is, R is equal to pi subset of A cross A. Definition 2. A relation R in a set A is called universal relation if each element of A is related to every element of A. That is, R is equal to A cross A. Both the empty relation and the universal relation are sometimes called trivial relations. Example, let A be the set of all students of a boys' school. Show that the relation R in A given by R is equal to A, B, A is sister of B, is the empty relation, and R dash is equal to A, B is the difference between the heights of A and B is less than 3 meters, is the universal relation. Solution. Since the school is boys' school, no student of the school can be sister of any student of the school. Hence, R is equal to pi, showing that R is the empty relation. It is also obvious that the difference between heights of any students of the school has to be less than 3 meters. This shows that R dash is equal to A cross A is the universal relation.
Remark. One of the most important relation which plays a significant role in mathematics is an equivalence relation. To study equivalence relation, we first consider three types of relations, namely reflexive, symmetric and transitive.
Definition 3. A relation R in a set A is called 1. Reflexive. If A, A belongs to R for every small a belongs to capital A. 2. Symmetric. If A1, A2 belongs to R implies that A2, A1 belongs to R for all A1, A2 belongs to capital A. 3. Transitive. If A1, A2 belongs to R and A2, A3 belongs to R implies that A1, A3 belongs to R for all small a1, a2 and a3 belongs to capital A. Definition 4. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. Example. Let L be the set of all lines in a plane and R be the relation L, defined as R is equal to L1, L2 is L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Solution: R is not reflexive as a line L1 cannot be perpendicular to itself. That is, L1, L1 does not belong to R. R is symmetric as L1, L2 belongs to R implies L1 is perpendicular to L2, which implies L2 is perpendicular to L1. That implies L2, L1 belongs to R. R is not transitive. Indeed, if L1 is perpendicular to L2 and L2 is perpendicular to L3, then L1 can never be perpendicular to L3. In fact, L1 is parallel to L3. That is, L1, L2 belongs to R. L2, L3 belongs to R. But L1, L3 does not belong to R.
Example, show that the relation R in the set 1, 2, 3 given by R equal to 1, 1, 2, 2, 3, 3, 1, 2 and 2, 3 is reflexive but neither symmetric nor transitive. Solution: R is reflexive since 1, 1, 2, 2 and 3, 3 lie in R. Also, R is not symmetric as 1, 2 belongs to R but 2, 1 not belongs to R. Similarly, R is not transitive as 1, 2 belongs to R and 2, 3 belongs to R but 1, 3 not belongs to R. Example, show that the relation R is the set of z integers given by R equal to a, b. 2 divides a minus b is an equivalence relation. Solution: R is reflexive as 2 divides a minus a for all a belongs to z. Further, if a, b belongs to R, then 2 divides a minus b. Therefore, 2 divides b minus a. Hence, b, a belongs to R, which shows that R is symmetric. Similarly, if a, b belongs to R and b, c belongs to R, then a minus b and b minus c are divisible by 2. Now, a minus c equal to a minus b plus b minus c is even. So, a minus c is divisible by 2. This shows that R is transitive. Thus, R is an equivalence relation in Z.
Let R be the relation defined in the set A is equal to 1, 2, 3, 4, 5, 6 and 7 by R is equal to A, B is both A and B are either odd or even. Show that R is an equivalence relation. Further, show that all the elements of the subset 1, 3, 5 and 7 are related to each other and all the elements of the subset 2, 4 and 6 are related to each other, but no element of the subset 1, 3, 5 and 7 is related to any elements of the subset 2, 4 and 6. Solution: given any element small a in capital A, both A and A must be either odd or even, so that A, A belongs to R. Further, A, B belongs to R implies both A and B must be either odd or even, which implies B, A belongs to R. Similarly, A, B belongs to R and B, C belongs to R implies all elements A, B and C must be either even or odd. Simultaneously implies A, C belongs to R. Hence, R is an equivalence relation. Further, all the elements of 1, 3, 5 and 7 are related to each other as all the elements of this subset are odd. Similarly, all the elements of the subset 2, 4 and 6 are related to each other as all of them are even.
Types of functions. Consider the functions f1, f2, f3 and f4 given by the following diagrams. In the figure, we observe that the images of distinct elements of x1 under the function f1 are distinct, but the image of two distinct elements 1 and 2 of x1 under f2 is same, namely b. Further, there are some elements like E and F in x2 which are not images of any element of x1 under f1, while all elements of x3 are images of some elements of x1 under f3. The above observations lead to the following definitions.
Definition 5. A function f x tends to y is defined be 1 minus 1 or injective if the images of distinct elements of x under f are distinct. That is, for every x1, x2 belongs to x, f of x1 equal to f of x2 implies x1 equal to x2. Otherwise, f is called many minus 1. The function f1 and f4 in figure 1 and 4 are 1 minus 1, and the function f2 and f3 in figure 2 and 3 are many minus 1. Definition 6. A function f x tends to y is said to be onto or subjective if every element of y is the image of some element of x under f. That is, for every y belongs to y, there exists an element x in x such that f of x equal to y. The function f3 and f4 in the figure 3, 4 are onto, and the function f1 in figure 1.2 first is not onto as elements e. F in x2 are not image of any element in x1 under f1. Definition 7. A function f x tends to y is said to be 1 to 1 and onto or bijective if f is the both 1 to 1 and onto. The function f4 in the figure 4 is 1 to 1 and onto.
Example. Let A be the set of all 50 students of class X in a school. Let function a to n be the function defined by f of x is equal to roll number of the student x. Show that f is 1 to 1 but not onto. Solution. No two different students of a class can have same roll number. Therefore, f must be 1 to 1. We can assume without any loss of generality that roll numbers of students are from 1 to 50. This implies that 51 in n is not roll number of any student of the class, so that 51 cannot be the image of any element of x under f. Hence, f is not onto.
Example. Show that the function f n tends to n given by f of x equal to 2x is 1 to 1 but not onto. Solution. The function f is 1 to 1 for f of x1 equal to f of x2 implies 2x1 equal to 2x2 implies x1 equal to x2. Further, f is not onto as for 1 belongs to n. There does not exist any x in n such that f of x equal to 2x equal to 1.
Prove that the function f r to r
Given by
f of x is equal to 2x is 1 to 1 and onto. Solution. F is 1 to 1 as f of x1 is equal to f of x2, which implies 2x1 is equal to 2x2, which implies x1 is equal to x2. Also, given any real number y in R, there exists y by 2 in R such that f of y by 2 is equal to 2 into y by 2 is equal to y. Hence, f is onto.
example, show that the function f n tends to n given by f of 1 equal to f of 2 equal to 1 and f of x equal to x minus 1 for every x greater than 2 is onto but not 1 to 1. Solution. F is not 1 to 1 as f of 1 equal to f of 2 equal to 1, but f is onto as given any y belongs to n, y not equal to 1, we can choose x as y plus 1 such that f of y plus 1 equal to y plus 1 minus 1 equal to y. Also, for 1 belongs to n, we have f of 1 equal to 1.
Composition of functions and invertible function. Consider the set A of all students who appeared in class 10 of a board examination in 2006. Each student appearing in the board examination is assigned a roll number by the board, which is written by the students in the answer script at the time of examination. In order to have confidentiality, the board arranges to deface the roll numbers of students in the answer scripts and assigns a fake code number to each roll number. Let B, subset of n, be the set of all roll numbers and C, subset of n, be the set of all code numbers. This gives rise to two functions, f from A to B and g from B to C, given by f of A, the roll number assigned to the student A, and g of B is equal to the code number assigned to the roll number B. In this process, each student is assigned a roll number through the function f, and each roll number is assigned a code number through the function g. Thus, by the combination of these two functions, each student is eventually attached to a code number. This leads to the following definition.
Example. Find g of f and f of g if f from R to R and g from R to R are given by f of x is equal to cos x and g of x is equal to 3x square. Show that g of f is not equal to f of g. Solution. We have g of f of x is equal to g of f of x is equal to g of cos x is equal to 3 into cos x whole square is equal to 3 cos square x. Similarly, f of g of x is equal to f of g of x is equal to f of 3x square is equal to cos 3x square. Note that 3 cos square x is not equal to cos 3x square, for x is equal to 0. Hence, g of f is not equal to f of g.
Example. Show that if f, A tends to B and G, B tends to C are onto, then GOF A tends to C is also onto. Solution. Given an arbitrary element Z belongs to C, there exists a pre-image Y of Z under G such that G of Y equal to Z, since G is onto. Further, for Y belongs to B, there exists an element X in A with f of x equal to y, since f is onto. Therefore, GOF of x equal to g of f of x equal to g of y equal to z, showing that GOF is onto. Definition 9. A function f, x tends to y, is defined to be invertible if there exists a function g, y tends to x, such that GOF equal to 1x and fog equal to iy. The function g is called the inverse of f and is denoted by f inverse minus 1.
Let y is equal to n square is small n belongs to capital N subset of n. Consider f from n to y as f of n is equal to n square. Show that f is invertible. Find the inverse of f. Solution. An arbitrary element y in y is of the form n square. For some small n belongs to capital N, this implies that small n is equal to root y. This gives the function g from y to n, defined by g of y is equal to root y. Now, g of f of n is equal to g of n square is equal to root n square is equal to n, and f of g of y is equal to f of root y is equal to root y whole square is equal to y, which shows that g of f is equal to I base n and f of g is equal to I base y. Hence, f is invertible with f inverse is equal to g.
Theorem. If f from x to y, g from y to z, and h from z to s are functions, then h of g of f is equal to h of g of f. Proof are shown on the screen.
Example. Let s is equal to 1, 2 and 3. Determine whether the function f from s to s defined as below have inverses. Find f inverse if it exists. A. F is equal to 1, 1, 2, 2 and 3, 3. B. F is equal to 1, 2, 2, 1 and 3, 1. C. F is equal to 1, 3, 3, 2 and 2, 1. Solution. A. It is easy to see that f is 1 to 1 and on 2, so that f is invertible with the inverse f inverse of f, given by f inverse is equal to 1, 1, 2, 2 and 3, 3 is equal to f. B. Since f of 2 is equal to f of 3 is equal to 1, f is not 1 to 1, so that f is not invertible. C. It is easy to see that f is 1 to 1 and on 2, so that f is invertible with f inverse is equal to 3, 1, 2, 3 and 1, 2.
Binary operations. You must have come across 4 fundamental operations, namely addition, subtraction, multiplication, and division. The main feature of these operations is that, given any two numbers a and b, we associate another a plus b or a minus b or ab or a by b, b not equal to 0. It is to be noted that only two numbers can be added or multiplied at a time.
Binary operations. When we need to add 3 numbers, we first add 2 numbers and the result is then added to the third number. Thus, addition, multiplication, subtraction and division are examples of binary operation, as binary means 2. If we want to have a general definition which can cover all these 4 operations, then the set of numbers is to be replaced by an arbitrary set x, and then general binary operation is nothing but association of any pair of elements a, b from x to the another element of x. This gives rise to a general definition as follows. Binary operations. Definition 10. A binary operation star on a set A is a function star A cross A tends to A. We denote star A comma B by A star B. Definition 11. A binary operation star on the set X is called commutative if A star B equal to B star A. For every A, B belongs to X. Definition 12. A binary operation star A cross A tends to A is said to be associative if A star B star C equal to A star B star C for every A, B, C belongs to A. Definition 13. Given a binary operation star A cross A tends to A and elements E belongs to A, if it exists, is called identity for the operation star if A star E equal to E star A for every A belongs to A. Definition 14. Given a binary operation star A cross A tends to A with the identity element E in A. An element A belongs to A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B equal to B star A and B is called the inverse of A and is denoted by A.
Example. Show that addition, subtraction and multiplication are binary operations on OR, but division is not a binary operation on OR. Further, show that the division is a binary operation on the set R of non-zero real numbers. Solution. Addition is R cross R to R is given by A comma B to A plus B. Subtraction is R cross R to R is given by A comma B to A minus B. Multiplication is R cross R to R is given by A comma B to AB. Since addition, subtraction and multiplication are functions, they are binary operations on R. But division is R cross R to R given by A comma B to A by B is a not function and hence a binary operation. As for B is equal to 0, A by B is not defined. However, division is R cross R to R given by A comma B to A by B is a function and hence a binary operation of R. Show that addition is R cross R to R and multiplication is R cross R to R are commutative binary operations, but subtraction is R cross R to R and division is R cross R to R are not commutative. Solution. Since A plus B is equal to B plus A and A into B is equal to B into A for all A comma B belongs to R. Addition and multiplication are commutative binary operation. However, subtraction is not commutative since 3 minus 4 is not equal to 4 minus 3. Similarly, 3 divided by 4 is not equal to 4 divided by 3. Shows that division is not commutative. Show that addition and multiplication are associative binary operation on OR, but subtraction is not associative on R. Division is not associative on R star. Solution. Addition and multiplication are associative since A plus B plus C is equal to A plus B plus C and A into B into C is equal to A into B into C for all A comma B comma C belongs to R. However, subtraction and division are not associative as 8 minus 5 minus 3 is not equal to 8 minus 5 minus 3 and 8 divided by 5 divided by 3 is not equal to 8 divided by 5 divided by 3. Show that 0 is the identity for addition on R and 1 is the identity for multiplication on R. But there is no identity element for the operations. Subtraction is R cross R to R and division is R star cross R star to R star. Solution. A plus 0 is equal to 0 plus A is equal to A and A into 1 is equal to A is equal to 1 into A. For all A belongs to R implies that 0 and 1 are identity elements for the operations addition and multiplication respectively. Further, there is no element E in R with A minus E is equal to E minus A for all A. Similarly, we cannot find any element E in R star such that A by E is equal to E by A for all A in R star. Hence, subtraction and division do not have identity element.
Example. If R1 and R2 are equivalence relations in a set A, show that R1 intersection R2 is also an equivalence relation. Solution. Since R1 and R2 are equivalence relations, A comma A belongs to R1 and A comma A belongs to R2 for every A belongs to A. This implies that A comma A belongs to R1 intersection R2 for every A showing R1 intersection R2 is reflexive. Further, A comma B belongs to R1 intersection R2, hence R1 intersection R2 is symmetric. Similarly, A, B belongs to R1 intersection R2 and B, C belongs to R1 intersection R2 implies A, C belongs to R1 and A, C belongs to R2 implies A, C belongs to R1 intersection R2. This shows that R1 intersection R2 is transitive. Thus, R1 intersection R2 is an equivalence relation.
Let R be a relation on the set A of the ordered pairs of positive integers defined by x, y, r into u, v if and only if xb is equal to yu. Show that R is an equivalence relation.
Example, consider a function f 0, pi by 2 tends to r given by f of x equal to sin x and g 0, pi by 2 tends to r given by g of x equal to cos x. Show that f and g are 1 to 1 but f plus g is not 1 to 1. Solution, since for any two distinct elements x1 and x2 in 0, pi by 2, sin x1 not equal to sin x2 and cos x1 not equal to cos x2, both f and g must be 1 to 1. But f plus g into 0 equal to sin 0 plus cos 0 equal to 1 and f plus g into pi by 2 equal to sin pi by 2 plus cos pi by 2 equal to 1. Therefore, f plus g is not 1 to 1.